This is my Hero 2021 robot that uses VEX components as well as a VEX Cortex microcontroller for the control of all the motors and sensors on the robot. And it can also use a laptop or a PC or even a Raspberry Pi 3 to control it in a tethered mode or an autonomous mode. It is controlled with a VEX Game Controller that allows me to move all the motors and servos, as well as use tank steering to move the robot around. Okay, I'm going to start the robot and show you how it moves around under control of a VEX Game Controller, which looks something like this. Okay, I'm going to turn on the robot. I have to be very careful so that I don't get hit by anything. Now I turn on the VEX Game Controller, and the VEXNET should connect. When all three green LEDs turn green, it's all connected and ready to be moved. So my first step will be to move forward. You can see how I can move very slowly, or I can go fast. And I can move backwards. I can turn using tank steering. I can turn the other way. Having a little bit of trouble probably because the battery's running out. Now I'm going to try to turn the arm. Now see, I move the arm up, or I can move it down. So I can point it towards an object and pick up like small objects. I can, so right now I'm moving it up and down in elevation. Oops. And that blue piece of metal in the back is a counterweight. And I can also move it in azimuth, so I can make it turn like a turntable. So I get a lot of motion from this robot. I have to be careful not to go too far, or I can damage the cables from the leading from the arm down to the main body. You can also see that I have some LEDs that act as like signals. So they can act like turn signals or warning signals. You can see the wrist here with the wrist motor and the gripper motor. The wrist uses a small gearbox, a small toy gearbox. Right now it's disconnected, but it does usually swing the wrist back and forth to give you another degree of freedom. And the gripper also moves up and down, opens and closes. Right now it's not working. I think I have a broken cable, so I have to repair that. But it usually opens and closes. And I put in a VEX potentiometer to measure how far open it is and how far closed it is, but I have not yet hooked up that sensor. A close-up of the mobile platform shows you the 4WD motion subsystem that drives the motor forward or backward or allows it to turn. You can also see one of the quadrature encoders on the left side. Here you can see the other quadrature encoder, the right quadrature encoder. These will allow me eventually to use PID control and dead reckoning and odometry to move the robot autonomously. Those are features that I'm working on currently. And those will be programmed using the Raspberry Pi 3 or a laptop or a PC tethered. With the Raspberry Pi 3, it'll be totally autonomous because I'll mount the Raspberry Pi 3 on the robot itself and connect it to the VEX Cortex microcontroller using the serial interface, using its UART1 and UART2 interfaces. I have all that code working. I have been able to, I designed and coded a serial interpreter that allows me to move all the motors and the arm and everything by sending it commands via the serial port from the Raspberry Pi 3. But still to do is the PID control for it, both for the having it being able to move in a straight line or move in a circular path, as well as also moving the arms and the grippers without damaging anything. Here you can see a VEX 393 motor, which is one of their upgraded motors, that uses a built-in quadrature encoder. And I'm going to use that to measure how far up or down in elevation the arm has moved. That way I can control it better without having to bang into the chassis or hit something. Here you can see the turntable, or should I say the azimuth drive motor, as well as its quadrature encoder that measures how many counts used to move it from 0 to 270 degrees. I don't go all the way to 360 degrees because then I would chop the cables and damage all the signals leading from the arm to the main chassis. In addition, I plan to add a limit switch to prevent it from going any further than 270 degrees or 0 degrees. That way I protect the cabling. Another feature are that I use bumper switches in both the front and back of the robot to prevent it from running, to stop it when it hits an object. Like if it bumps into my leg or bumps into a wall, it'll stop the robot immediately. This is a great safety feature. You can also see that I can turn on or turn off the LED. The LEDs are a great diagnostic feature, and all you do is you just connect them to the digital outputs and just hook up the anode to the positive to the signal end of the digital output port, and hook up the cathode to ground. And the LED will work perfectly, and it doesn't need a limiting resistor since those are built into the VEX Cortex. This is the drivetrain. I have 4 subassemblies using the VEX motor and the medium-sized gear and the large-sized gear to provide more torque and power for the robot to move, like on rugs or even outdoors. This robot can move even on outside in a garden with short grass. I've even had it moving in snow, as long as it was very hard-packed snow. This is the front side of the robot. You can see the two VEX ultrasonic rangers that I'm going to be using eventually when it runs autonomously for obstacle detection and obstacle avoidance and navigation. With these sensors, I can detect objects up to 80 centimeters away, which is quite a nice feature. Given that this robot is pretty heavy and it could hurt my dog or bump into me and scratch me, it's a pretty heavy robot. You can also see that I used other components other than VEX components. Hardware that I bought at hardware stores such as Lowe's or Home Depot, which includes some of the brackets used. You can see some of the brackets right there, as well as I also use scrap metal sheets, which are very light. They're light aluminum, but they're very rigid, and they made a great platform for the arm. Additionally, I used Lazy Susan to provide the arm really smooth motion and when it moves in azimuth from 0 to 270 degrees. So the between those two copper plates, there's a small Lazy Susan with ball bearings, which gives it very smooth motion. You can also see all the wiring connected to the VEX microcontroller, the VEX Cortex. It's pretty messy because there's a lot of wires from all the sensors and motors. And to power the robot, this whole robot is being powered by that little 9-volt battery pack, although you can use the 7.6 volt RC batteries that Innovations First, the manufacturers of VEX, provide. I found that it can work with the 9-volt battery pretty well too, as well as 12 volts. I've been able to power my robots using a small 12-volt SLA batteries, which are rechargeable and far more durable than the VEX ones. But they're also heavier. Here you can see the gearing that I used for the elevation arm. It uses a very large gear, 2 pairs of large gears and medium gears, both for durability so that they don't get stripped, and also to provide enough torque to lift small objects with the arm. And you can see the blue counterweight. For the arm, so that balances the motor so it can pick up objects without damaging the motor and the gears. In order to program this robot, I used Robot C on the VEX Cortex end, and I used C and Ada on the PC and laptop and Raspberry Pi 3 end. For the autonomous navigation, I'll be running C and Ada applications that I use to code the algorithms, such as PID control. Well, actually, PID control will be done in Robot C on the VEX Cortex, but higher navigational algorithms like wall following and PID, not PID, sorry. I will use Ada for the navigational algorithms, running the navigation algorithms and safety algorithms. This robot is pretty good size, so it's a good application to use Ada for safety. Ada is a language that has been around for quite a few years. It's not as popular as C or C++ or Python, but it generates very reliable code. And it's great for embedded systems such as robots because of its safety features, including very tight type checking and constraint range checking. And it also provides tasking, a tasking model, which is very nice to be able to run multiple tasks under control, and they can all be developed in Ada, and they, very nicely. Some other features like that make Ada. That's why I chose Ada for this robotics application. But I also have some C routines. In fact, Ada can call C routines, and it can call C++ routines. So I also had some code written in C and C++, like for drivers, such as the serial communications and some of the I2C sensors that I'm going to be adding on, and other sensors, like XYZ accelerometers, etc. So using VEXNET and the VEX Game Controller, I can communicate to the VEX Cortex and move all the motors control the robot very nicely. And this is using Wi-Fi. This is Innovation's First, or VEX's own version of Wi-Fi, which is used also in their school contests and things like that. The VEX Cortex is an older microcontroller, but it's still very powerful, even though, and you can buy it reasonably on eBay because, it's been discontinued. In fact, some of my other robots use even the old VEX 0.5 microcontroller. It's still a really good controller for small robots. This robot here had too many sensors and motors and everything to use the VEX 0.5 microcontroller. This one gives you 2 extra motor ports, and it allows you to control 2 DC motors. Right now my DC motors are hooked up to the wrist and to the gripper, but I don't have enough power. The 9-volt battery is running out, so there's not enough power to move them. But everything else is working. And you have to really be very careful not to make sudden jumps with the joysticks, because it's very sensitive. So you have to be very slow, very careful. And right now I don't have the sensors to detect whether it's exceeded the mechanical limits. These would be limit switches and that red potentiometer on the gripper, as well as the quadrature encoder on the azimuth motor. Because otherwise, as you can see, I could cut the cable accidentally. You can see how responsive this robot is, and it is capable of picking up objects. I can't really demonstrate that right now because of the trouble I'm having with the battery and the DC motors. But it does turn. It does work outside, and with a fresh battery, it moves very quickly. You'd be surprised how fast this robot can move, being four-wheel drive. This is the controller, the VEX controller, game controller. You can see it has 2 joysticks as well as 12 small push-button switches, 8 in the front and 4 in the back.